Welcome back, ladies and gentlemen. Today we're going to take care of section 5.2, and it deals with perpendicular bisectors and properties of, and something called a circumcenter. Up on the screen you'll see your exit question that you can fill out in the Google form on my website. To start off, I'm going to start off with a little bit of vocab. You need to know what these three words mean. Equidistant we've already talked about in terms of regular shapes, meaning the same distance. Perpendicular bisector, technically we haven't defined yet, but it's a bisector that's perpendicular to whatever it's bisecting. So there's your official definition: a figure, a plane, line, ray, or segment that is perpendicular to a segment, so you can only chop a segment in half, at the segment's midpoint. So it has to be both perpendicular and bisect the segment. And then lastly, a point of concurrency. And we've talked about an intersection. Well, a point of concurrency is just like a mega intersection where there are more than two things, or three or more things intersecting at a concurrent point. All right, and then to go along with those vocabulary words, we have two theorems today. We're actually going to have a third, I believe, as well. But we have a perpendicular bisector theorem, which says that if you have a segment AB and you construct the perpendicular bisector of it, and then you choose a point C anywhere on that perpendicular bisector, that point C is equidistant from A and B. So the drawing looks like a little something like this. So if you have this situation, you know that C is equidistant from A and B. You can also pretty easily see that this would be a good one for a converse to have. So theorem 5.3 is just the converse of that, in that if you have a point that is equidistant from A and B, so a point that's equidistant from 2 points, then you know that point must exist on the perpendicular bisector of the segment or hypothetical segment that would connect AB. Using those two theorems for today, you can do this problem. Why don't you pause the video and see if you can find those dimensions. To find Kn, we know that we are given that JK is a perpendicular bisector, so we have this point K that exists on that perpendicular bisector. So because of theorem 5.2, we know that K is equidistant from N and L, so we can set those two expressions equal to each other. Solve it. You get x equals 3. They didn't ask for x, they asked for Kn, I believe, right? And plug it into the formula, substitute the value in, and you'll get 13. And then the second question is, what must be true of M? Well, M, you can see, is this point right here, and it is equidistant from both L and N. So basically the only thing you can say is that it must be on this line. If this line were to be extended, it would go directly through M. Okay, now we know what a perpendicular bisector is. Now I'm going to do a little something on GeoGebra with using perpendicular bisectors. So what I'm going to do is I'm going to draw a triangle, and I am going to use this tool right here that constructs the perpendicular bisectors, and I'm going to do that for each side. And as I do one, you'll notice that the program creates a point in the middle and then makes a perpendicular line for it. I'll do another one right there, and you'll notice that the two lines intersect, and that shouldn't be anything special. Any two non-parallel lines will intersect each other. But you'll notice that when I do a third one, the third one intersects at the same intersection. So there we have one of those points of concurrency there where we have more than two things intersecting. Now, this triangle that I drew was not special in any way, so I can move this triangle around, and you can see that that point of concurrency always exists. Those three lines always intersect at the exact same point. The other thing you'll notice is that that point of concurrency is not bound within the triangle. So if I change the shape of the triangle, the location of the point of concurrency can change. And it has a couple special properties to that, in that if the triangle right here is obtuse, you'll notice that the point of concurrency is outside the triangle. If I swing back to an acute style triangle, you'll notice that the point of concurrency is inside the triangle. And there must be some threshold where it's on the triangle too, so if I bump that so it's approximately equal to that, or right on the triangle, you notice that I have pretty much a right triangle, and the point of concurrency occurs on the hypotenuse. The final property of this point of concurrency that I want to show you is I'm going to grab a circle tool, and I'm going to define that circle on the center right there, and I'm going to pull this out to one of the vertices of the triangle. And you'll notice that this circle comes around and it actually hits all three vertices of that triangle. So this point of concurrency is equidistant from all vertices of the triangle. I can demonstrate that further by drawing in the segments from, basically I'm going to go from the center of the circle to each vertex. So I'm going to create 3 segments, and if you give me a moment, I'll format them so we can see them more clearly. Okay, I'm back, and as you can see, those segments that I was talking about are a different color now, and you'll notice as I manipulate the triangle, those 3 segments, those 3 distances between the vertex and the circumcenter are always the same length. So no matter how I change the shape of the triangle, the lengths of the blue segments basically are all equivalent always, no matter what. So from this drawing, we can come up with a couple patterns that we've noticed. One is that if we do construct these perpendicular bisectors, they do intersect at a point of concurrency. Second, that point of concurrency is the location of it is related to what style of triangle it's within or constructed with. And thirdly, that point of concurrency is equidistant from each vertex. So that's basically the stuff you need to know for 5.2. And here you will see the official vocabulary. So a circumcenter is a point of concurrency constructed from perpendicular bisectors. And as we saw with the software program, that those 3 red segments on this one are equivalent in length. So you have a theorem saying that the point of concurrency exists and those distances are the same. So there's theorem 5.4 for you. And the other word I threw in there was inscribed. And inscribed means the vertexes of whatever polygon, all of them happen to be on the circle. So you can inscribe a triangle, a square, a rectangle, etc. But as long as all the vertices lie on the circle, we call that an inscribed polygon, or in this case, an inscribed triangle within the circle. It's a word that we're going to use, so you got to know it. Secondly, we also played around with the shape or the type of triangle that we're playing with, and this is a quick summary of that. If you have an acute, the circumcenter is inside the triangle. If you have a right triangle, the circumcenter is on the hypotenuse, and if you have an obtuse triangle, the circumcenter is on the outside of the triangle. Now, this is actually one of those things in math that's actually useful. So let's say you're a logistics company. You ship things from one place to another. Three of the largest markets in the United States are New York City, Seattle, and Los Angeles. And inconveniently for you, they are located on the opposite sides of the country. So if you were to create this mega shipping hub, where would you create it? Well, you'd want it to be equidistant and hopefully the shortest distance from all 3 of those. And you can do that by figuring out where the circumcenter is, and that way you're not giving any preference to, say, New York City over Seattle or Los Angeles. So you'll be treating each of your 3 major markets equally. So you can literally take this map, plop it into GeoGebra, and do that perpendicular bisector thing by creating all 3 perpendicular bisectors, and you'll notice that they will intersect at a common point. And at that common point, that's where you should put your company. And you'll notice that it intersects in northeast Nebraska, and you look at the map of the United States and hey, look at that. That's why Omaha exists. If you've ever been through Omaha, there's an awful lot of trucking companies. We can also ask you to do more traditional geometry style problems. So here's a drawing, here's some givens. Why don't you pause the video here and find those 4 distances that I've asked you to find. All right, first up, let's go for the easy stuff first. BE is actually a very easy question because E, given that G is a circumcenter, that means that this right here is a perpendicular bisector, which means that E is a midpoint. So if this distance is 6, then also is BE. Next up, we need to figure out what AG, BG, and CG is, but those are all the same because they are all equidistant from each vertex from Theorem 5.4. So as soon as we have one, then we have the others. So we look at the information that we can have from there, and we have a couple of numbers over here that we haven't used yet. And if we look closer at that triangle, we'll also notice that it is a right triangle because, again, this is a perpendicular bisector right here. Even though it wasn't labeled so in the drawing, because it's a circumcenter, that is a perpendicular set of lines there. Which means we have a right triangle, which means we can use Pythagorean theorem and solve it. And then we'll have 8.5 being the length of BG. and all three of those are the same length. So we can just list them as such in one statement like that. I'll see you in class. There's the homework assignment. Remember to bring a compass and a straight edge tomorrow if you have one.